Thank you very much, and thank you for the invitation. Yes, I want to talk about a paper that I posted last year, which is essentially about the existence of canonical metrics for families of projective varieties. So I'm going to explain what that is with the hopes of like stating the theorem and kind of like giving an idea of what this is all about. So to start, let's start with like the motivation. So a central problem in complex geometry is the existence of certain canonical halometrics. Also, if you have any questions, feel free to interrupt me all the time. Yes, so in my case specifically, we wish to find necessary and sufficient conditions on a so-called polarized manifold, which I will denote with X and L. A polarized manifold is, for me, a projective manifold together with a conscious choice of ample line bundle, which I call the polarization. The classical example are, for example, Fano varieties, where the polarization is the anti-canonical line bundle. Same with, for example, canonically polarized varieties. Yeah. On a polarized manifold such that there exists a halometric, which I will denote with omega, contained in the first Chern class. You can see as a class in the second, the Ram cohomology of my manifold, satisfying certain canonical or, in quotation marks, special curvature properties. In a few talks, we have seen some of these examples of these special properties in curvature. Specifically, the examples that I'm interested in are, for one, halometrics for which the Ricci curvature is a scalar multiple of my Kähler metric, which are also called Kähler-Einstein metrics. Short KE metrics. A more general example are halometrics for which the scalar curvature is constant, where S hat is also known as the average scalar curvature of a given Kähler class, which is constant for any choice of Kähler metric. So what I'm really asking here is that the scalar curvature is literally constant. And we call these constant scalar curvature Kähler metrics, which in short is CSCK metrics. And finally, even more general than these two cases, and which will be the case of interest, are so-called extremal metrics, which are metrics that satisfy the following condition. I want that del bar of the 1O part of the gradient with respect to my metric of the scalar curvature viewed as a function is 0. And these are called extremal metrics. Note that any Kähler-Einstein metric has constant scalar curvature by definition, if you want, but also in turn, any CSCK metric is extremal because this gradient would be 0. Exactly. The leading conjecture in this entire story of the existence of canonical Kähler metrics is the following. Or the leading problem is the so-called Yao-Qian-Donaldson conjecture. Which goes as follows. Conjecture, also commonly abbreviated with YTD, saying that such a polarized manifold admits a CSCK metric. So XL is CSCK. If and only if this pair is what we call K polystable. I will explain in a second. So for one, on one hand, let me write it like so. K stability in general, I will not go into the details what K stability is, but roughly it is a stability condition that is algebra-geometric in nature for manifolds. So for people who are more into vector bundles, this is sort of comparable to slope stability. And this kind of conjecture that we have here would be a theorem for vector bundles, the Hitchin-Kobayashi correspondence, saying that I have a Hermite-Einstein metric if and only if your slope semi-stable or slope stable. Yeah. Okay, let me write that down. So K stability is an algebra geometric stability condition which involving so-called test configurations. Which are families over the complex numbers such that the general fiber is isomorphic to my polarized manifold and admits or is endowed with a C-star action such that my central fiber sort of becomes a C-star equivariant degeneration of my test configuration. And to define, for example, K semi-stability, I want that the Donaldson-Futaki invariant which I denote with df of curly x curly L is non-negative. For people who know a bit of GIT, these test configurations would be one parameter subgroups in line with the what is it called? Now I forgot the name. The Mumford criterion, the Hilbert-Mumford criterion. Thank you, and the weight that is associated to the one parameter subgroup. So I just want that to be non-negative. Exactly. On the other hand, CSCK metrics are essentially a solution to a partial differential equation. So what we're saying is that a certain algebra geometric condition implies that I can solve a certain geometric PDE. About the conjecture, I want to note that one direction is known, which is this one. This direction is known, where works by Stoppa, Donaldson, and add Bergman. And the entire conjecture is known for Fano varieties, let me write that in purple, for Fanos. That is the famous Chen Donaldson son theorem. There's also an exciting recent development by Matthias Jonsson and Sebastian Buxon that proved the entire conjecture when you replace K polystability with what is called K hat polystability, which sort of is a form that tests over more things than test configuration. That uses non-Archimedean geometry. But since this is like not the part of what I want to talk about, I'll just leave it less so. But yeah. All right. Yes. So what do I want to do in my case? So we have this equivalent for manifolds. And the question that I'm interested in is the following. Can we generalize this? For families. XL over delta star, where delta star is the punctured open disk. In a complex plane. So instead of like just looking at one projective variety, I look at a family, and the important point is that this family doesn't have to be trivial. So we can look can have different fibers. Yeah, this question is interesting. So why are we doing this? It's interesting for two reasons I give. For one, I want to construct moduli spaces parametrizing projective varieties. So construction of moduli spaces of varieties. In this case, whenever we want to construct moduli spaces, we naturally have to ask ourselves questions about families of varieties of the class that we want to parameterize. In this case, it would be pairs of a complex manifold together with a choice of ample line bundle. And what we're doing is that we're interested in the so-called evaluative criterion for separatedness. So when I construct moduli spaces, I want them to be separated, and I can translate that to a question about families of my varieties, specifically given a family XL over the punctured disk of polarized varieties of a certain class. So this class of varieties could be like, for example, all varieties that admit a CSCK metric or varieties that are K polystable. We want that there is at most one filling, which I will call curly X curly L again, to the whole disk. Note that this, in a quite literal sense, means that the corresponding moduli space, provided we have it, is separated, because having at most one filling really means that we have no double points. On the other hand, when I require that I have, for example, at least one filling, I'm essentially asking that my corresponding moduli space is compact. So this would be like the evaluative criterion for compactness or properness of moduli spaces. All right. The second reason this question is interesting is the following. Problem. Which algebra geometric conditions does a filling XL of XL satisfy such that the central fiber, which I will denote with curly X0 and curly L0, which is now a literal polarized variety. So I say variety because since we're looking at degenerations, they can be singular. And in general, they can also be non-reduced and non-irreducible, I think. And yeah, the question I'm interested in is that such that the central fiber is smooth and admits a canonical geometric. So these are the two things. Also for terminology, I was talking about fillings here and here. For the purpose of these talks, such fillings are called models of XL. Yeah, and I will use models from now on. All right. So how do we tackle this problem? We tackle this problem using the so-called Chow-Mumford abbreviated CM, which is the CM from the title that we're interested in, line bundle. Specifically, given a model, or more generally, given any family over a base B, I think the only assumption that I need on B is that it's irreducible, but I'm not quite sure. Doesn't matter for this case, but for any such flat family, together with a relatively ample line bundle, we have a Q line bundle, which I will denote with lambda CM over the base. This is the CM line bundle. And yeah, for any such family, I can construct such a line bundle. I will not go into the precise construction of this line bundle. It doesn't really matter. It uses like push forwards of my line bundle along this structure morphism when I have, and the so-called Knudsen-Mumford expansion of this into Q line bundles on my base. But I'll leave it as so. The important example is that, for example, if my base is a proper curve. Say again? Yeah, pretty much. Yep. Yeah, I want the determinant of the push forward of KL. quite literally. Yeah. So if I have a proper curve, we can define the CM degree, which I denote as CM of curly X curly L, which then is the degree of my Champlain third line bundle over the curve. The question that we're doing now is the following. So given a family XL, which models minimize the CM degree? And we will soon see that this corresponds to the existence of CSCK and extremal metrics, sort of in the spirit of the Yao-Chan-Donaldson conjecture, where minimizing the CM degree should serve as our algebro-geometric condition that we want. Yes. So the main theorem that I want to present, let me do it now, is the following. I will state it, and then I will use the rest of the lecture to kind of explain what the statement means, and then learn some things about the techniques of this. And the theorem goes as follows. So we need some setup. So let T, or let's hope I have enough space. Let T be a maximal torus in the automorphism group of XL, my family, such that the fibers are preserved. So I'm interested in automorphisms that are parallel. And let curly X and curly L, curly X, curly L, and curly X prime, curly L prime be so-called T equivariant of XL. An equivariant model is just a model that comes with a torus action that such that the restriction of my torus action on XL is the same. So I kind of want to extend the torus action that I have, since these are fillings. And assume that the following hold, that the restricted torus, so if I have a torus action on my entire model, I get a torus action, a restricted torus action in the automorphism group of my central fiber. And I want that to be maximal. It's maximal. Note that this is not automatic because, for example, for test configurations, you could look at, I think it works when you look at elliptic curves with trivial automorphism group, and you can degenerate it to something that has more automorphisms. So you have to be careful here. So I assume that. But the more important part that I'm interested in is the following. And the central fiber is smooth and admits an extremal metric. Yes. So I have my assumption of an canonical metric in my central fiber. Then there exists a one-parameter subgroup, called psi, in my torus, such that the CM degree of the twisted model of XL, whatever that means so far, is smaller or equal than the CM degree of any other model that I'm choosing. So here I have some sort of minimization of CM degree. But I can say more, where the inequality is strict whenever, what do I want? Whenever for any one parameter subgroup, let's call them beta in T, we have that the twisted model of curly XB, curly L beta is not isomorphic to curly X, curly L. So I also get some sort of strict minimization. Okay, that's the theorem. Now kind of want to explain what all the words here mean. If you have any questions, also just let me know. Yeah. Say again? Yeah. You mean like the torus inside the automorphism group or the automorphism group itself? Yeah. Oh, so yes, yeah, exactly. So I swept some things under the rug. So when I say I have automorphisms that are parallel here, and I say I have a maximal torus, what I'm really getting is a torus that is a fibration over my my punctured disk, meaning that for any fiber, I get, let's call it torus, that is inside my automorphism group in that fiber. So I need some flatness assumption on what I call a torus. Yeah. This will be important when I define the twist, which we'll do right now. Yeah. Yes, yeah, for example, like I can produce different models using blowups. Yeah. Yeah, no, it's good. That's good. Say again? Yes. So yeah, what I'm saying is that curly X, curly L is specific. Like I want it such that the central fiber has this metric. And then I'm saying that the CM degree or some kind of twisted version is minimized for any other choice. So curly X prime is arbitrary. Yeah. This is not quite the technique that goes into proving this. Yes. Yes. No, you're not. Okay, I will explain what twisting is. The general fiber stays the same. What changes is the identification over the general fiber. So yeah, that. Okay, now I understand. Yep. Yeah, the central fiber stays the same, and that's important. All right. Given. Okay, let me first explain this twisting. So given a one parameter subgroup, beta in T, which we really should think of, again, kind of like a fibration over the punctured disk. That means that for all T non-zero, I get an automorphism or an automorphism of this fiber here. We define the twist curly X beta curly L beta of curly X curly L to be the same model. So I don't change anything about the geometry itself, but I change the same model, but we change the identification. Yeah. The identification of the general fiber. Let me write it like so. Of my family with the general fiber. So one detail that I haven't mentioned when talking about fillings or models is that abstractly, when I want a filling, I technically also need to choose an explicit isomorphism that comes between like the this restriction of my family over the punctured disk and the thing that I started with. Kind of this is often implicit, but in our case, especially when we define like CM degrees, these choices of isomorphisms will be very crucial. Yeah. For example, when you look at test configurations, you choose an isomorphism over the one fiber and use the C star action to get an identification over the entire C star. But that still depends on an identification and the C star action. Since we don't have a C star action here, we need to choose an identification over the entire thing. What the one parameter subgroup does essentially is that I change this isomorphism by composing it with another isomorphism that on the level of fibers is just this automorphism that we have here. That makes sense. So this is like automorphism induced by beta on each fiber. I'm changing the identification. In particular, the central fiber stays the same. Before I go into like some more details of the theorem, I also want to point out like an important consequence of this theorem, which is sort of like an answer to the first motivation of the question about moduli spaces, which is that the theorem gives a numerical proof, numerical as in a sense of quantitative CM degrees, numerical proof for separatedness of the moduli space of extremal manifolds, say together with a fixed torus. This moduli space has already been constructed by Fujiki and Schumacher in the 90s, and we know that it's separated. But what we're saying here is technically something that is stronger than just separateness. And the way you can recover separateness of the moduli space in line with this separateness criterion is the following. So let's start with a family of polarized varieties that have an extremal metric. So I want to look at a family within my moduli space. And I want to prove that there's at most one extremal filling. Okay, so assume that we have two extremal fillings, and we call them curly x, curly L, and curly x prime, curly L prime. What this theorem says is that there exists the CM degree in one direction is minimized, but also since the second model also has an extremal metric, I also know that the other direction is minimized, while the central fiber is unchanged. So what this twisting does is that it doesn't change how the models look like. But now I know that the CM degree is equal. So now I have the strict inequality assumption here. meaning that there exists a one-parameter subgroup such that these twists are isomorphic. But since the twist doesn't change the models itself, I'm just saying that the models are isomorphic. So I have at most one filling, and in turn, I get separateness of my moduli space. The CM minimization, yes. Yeah, it does. I can say it right now, just like as an example. It quite literally does. With the change that in K-stability, we're essentially looking at trivial families. And for CM minimization, we generalize that to families that cannot be, that do not have to be trivial. Specifically, you can write it like so. So like within K-stability, for a test configuration, so take a test configuration, curly X, curly L, of, now I want to use XL for a family. So now I want a literal like X1, L1, so like a genuine polarized manifold, and a test configuration of it, which we can see as a model of the trivial family, because a test configuration is just trivial outside of the central fiber. So now we can see how this like non-triviality of my family comes into play over there. We have that the Donaldson-Futaki invariant of my test configuration is equal to the difference of CM degrees of my test configuration seen as a model. So this is a model, and this is not just any model, this is a model of the trivial family, X1 cross delta star L1 minus, since I have a trivial family, I also have a trivial model, which is filling the central fiber by the same thing. So I get the trivial model here. And what I'm saying here is that the Donaldson-Futaki invariant is the difference of CM degrees of these two models. So why does this matter? When we compare this to the CM minimization that we have over there, ignoring the twists, what I'm saying is that a polarized manifold, X1, L1, is K semi-stable, if and only if the Donaldson-Futaki invariant is non-negative. But this means that this manifold minimizes my minimizes the CM degree. At the same time, I want to ask questions about minimization and the central fiber admitting a certain special calometric. In this case, this is the thing that I'm minimizing. So I have a special calometric on the central fiber of this, but this is just this manifold over here. So I get Gaussian-Donaldson in a sense again, because I'm asking about the existence of a calometric over here. This is how these two things interplay. Exactly. How much time do I have? 50 minutes, okay. Yeah. Yes, so this is an interesting open question. So for example, you could ask, so the question was like whether like finding a minimizer has to do something with like K-stability. An interesting question that you could ask is, let curly X, curly L be a model, and assume that this model minimizes the CM degree for all other models. Is it true that the central fiber must be K polystable? That is open, but a very interesting question. Sort of like a converse to what I'm just saying here. Yeah, but it would be nice to have an equivalence. In other words, also what this theorem says is, I already erased Gaussian-Donaldson, but I was saying that one direction is known, where like CSEK implies K polystability. This is like sort of like an analogous statement for families. Like I have a canonical metric and I get an algebra geometric stability condition. Yeah. So this is the family equivalent. what else do I want to say? Furthermore, yes. The theorem, oh yeah. Furthermore, the theorem is also a generalization of a theorem by Masafumi Hattori from, I believe, 2024, who proved CM minimization for CSCK manifolds or CSCK fillings links that extend to a proper curve. So CSCK is a special case of extremal. What happens in that case is that we get rid of the twisting, we get rid of the C-star equivariance, and we get literal CM minimization, where the inequality is strict if and only if the models are not isomorphic. So this theorem is a generalization of that. It is not only a generalization for CSCK manifolds, but also for families that do not extend over a proper curve. So something that is entirely non-clear at the moment, and someone could have asked the question, is what is the CM degree when we have models that are defined over the open disk? So I was saying over here that if I have a proper curve, I can define the CM degree here. But in my theorem, I have families that are over a non-compact base. So how do I make sense of the degree if I, for example, in an algebra geometric sense, cannot take intersection numbers? So a priori, this doesn't make sense at all. And I will use the rest to explain how this makes sense for these non-proper bases. So the base B equal to delta is not compact. So a priori, we cannot make sense of the degree. That's bad. But however, given two models, which is the case that we're interested in, we can identify the difference of CM line bundles so I have the CM line bundle for one model and the CM line bundle for the other model. And what I'm saying is that the difference of CM line bundles can be identified with a number. And this is using the chosen isomorphisms with the family that I'm starting with. So to define the difference of CM degrees, this thing will be very important. This identification will be very important. Yep, so let's do that. So how does this work? If I have an identification of this model with this model, to XL, but then I, of course, have an identification of these. I haven't explained the precise construction of the Chow-Mumford line bundle, but yes, I have mentioned that it like involves the determinant of the push forward of my polarization. So what's happening is that this implies that we also get a chosen isomorphism between my CM line bundles. Over the punctured disk, since this is only an isomorphism over the punctured disk. In other words, when I take global sections, I obtain an isomorphism between those two, which I will call capital phi. And that's an isomorphism. Note that any section over the entire disk, so not only the punctured disk, is contained, of course, in the punctured disk. But this isomorphism does not imply that this does have to lie in this. So a priori, the image of global sections that extend are only contained in here. But this is what I'm going to use to associate a number to this construction. So what I do is let S be a section over the entire disk, and I assume that it's trivializing. Meaning that it's nowhere vanishing. And then and let lambda, which is an integer, be the maximal integer such that t minus lambda of the push forward. Okay, maybe I should write it like so. This is my, let me write it like so. Phi is my isomorphism. This is my push forward of S, which a priori is just a section on the punctured disk, but I want that it is contained in the entire disk so that it extends the entire disk. Here, T is like where this is like the parameter of the parameter like T in delta. And so I can look at it as like a regular function on the entire disk. And what I'm essentially asking for is the order of my push forward. So the push forward is a section on the punctured disk. I can ask what the order is at T is equal to 0. This maximal number lambda is that order. Definition. The difference of CM degrees between curly x and curly L and curly x prime, curly L prime is something that I, as symbols, denote as this difference. And I define it to be this exact number, lambda, that I want. Yes. Now we also can make sense of this difference in the sense that I'm saying that the CM degree of one model is lower than the other if the difference is non-positive or non-negative. So this is the way I can make sense of inequalities by just asking that the difference satisfies an inequality. So this is how we make sense of this. As a final remark, which I've like, say again, for a proper curve, you don't. Like the reason I mentioned this is not only because it's straightforward, but also this is the way the theorem was phrased in Hattori's result. So he used models that extend to a proper curve, used the easier definition of the degree, and proved the case in that case. So really, one of the selling points of the new theorem is that it also works for non-proper bases using this definition. Note in the case when the model does extend to a proper curve, these numbers agree, and so on. So this is a genuine generalization and part of the theorem. Yes. Let me write that down. Remark, note that the number lambda depends on the choice of isomorphism phi. In particular, if I change this isomorphism, I get a different number, meaning that if I twist models, which means I change the identification, I also change the number, even though I'm not changing like the geometry of my model itself. So this inequality is also different. Yes. But yeah, maybe a final remark. Yeah. No, I think this is all. Yeah, let me just stop here. Thank you.
Thank you very much. Are there questions?
Have you tried thinking about this from the point of view of non-Archimedean geometry, non-Archimedean Kähler geometry?
Oh, that is a very good question. And yes, you can. So what you can do is in non-Archimedean geometry, you have a functional known as the Mabuchi functional, where you're interested in the slope of the Mabuchi functional at infinity, which you can express as some non-Archimedean value for a test configuration. You can do the same thing, noting that for this association of a test configuration to this like function that you evaluate at the non-Archimedean Mabuchi functional is essentially a construction that compares the test configuration with the trivial test configuration. If I have two models, I can just compare these two models, construct a function depending on those two models the same way, and ask if like the geodesics of my Mabuchi functional at the slope at infinity is those two models. Rémi Riboulet has like written a thesis about this sort of problem. An interesting question there is this non-Archimedean Mabuchi that I just constructed equal to the difference of CM degrees? And that would be like the equivalent of like saying if the non-Archimedean Mabuchi is the Donaldson-Futaki invariant.
So in your theorem, so that twisting factor psi, that is a one parameter subgroup inside the Torah. So is that unique? So you get that?
Say again, is that one parameter subgroup in?
No, I am asking, is it unique or you get a?
Is it unique? Yeah, it's unique in the sense that it's explicit. Like I'm saying, I'm constructing one parameter subgroup depending on my two models, and say that for this one parameter subgroup, this inequality is.
Okay.
So it's unique in the sense that it's explicitly constructed. One person has once asked me if this one parameter subgroup corresponds to the extremal vector field, for those people who know it, of my central fiber. The answer is no. The extremal vector field is something that doesn't depend on the other model, but I'm constructing something that does depend on the other model, so they're not the same. Yeah.
Okay, so any kind of inverse directions, I suppose you have this inequality and also like so for every kind of model, so do we expect like a extremal matrix in that? I mean, like the central fiber kind of thing.
Are you asking about the converse?
Yes.
That is an interesting open question, and like very related to Yao-Chan Donaldson, where I want to go in the other direction. So essentially, what I'm asking is that a certain algebrogeometric stability condition implies that I can solve a PDE, and that's difficult. And in this case,
and for CSEK matrix, so you are saying you do not need any kind of this twisting factor, right?
Say again?
or constant Clark curvature matrix. So you do not need any twisting factor, right?
You do not need any twisting. The reason you do not need any twisting is that essentially what this twisting does is that I add a Futaki invariant of my one-parameter subgroup. And a theorem by Futaki says that the Futaki invariant vanishes for all parameter subgroup provided you're CSCK, meaning that this twisting just falls away. In other words, if I replace Extremal with CSCK here, I can just kill this one-parameter subgroup because the numbers with twisting is the same.
Okay, okay. Thank you.
It's an Extremal feature.
There's no more question, then let's thank Gabriel.